Yeah. Sunday is when the homework is due, and we're talking about water softening today. We've talked a little bit about water hardness in a previous lecture. Anybody remember what that definition of hardness is for water? What causes hard water? What's that? One more time? Oh, temperature. No, I don't think it's affected by temperature, except that if you have usually warmer water will precipitate some of the calcium carbonate. And so temperature can have an effect on how much calcium carbonate's in the water. Okay. Yeah, in an aquarium? Okay. So he mentioned that if you put rocks in an aquarium, that it will change the hardness of the water there. And we've talked about two main kinds of water so far. There's surface water, which means water that comes from lakes and streams. And what's the other kind? Groundwater. And so groundwater is in the aquifer. It's touching soil, it's touching rocks, and the chemicals that are in the rocks and the soil will dissolve into the water. You know, the water that gets down underground, it will stay there for hundreds and sometimes thousands of years before we pump it out. You know, it rains into the mountains, it rains onto the soil, the water infiltrates down underground, and it can stay there for a very, very long time, depending on how quickly we pump it out and how much rainfall there is. And so the water that touches the rocks has the same characteristics of the rocks. And calcium contributes to hardness, magnesium contributes to hardness, and those are the two main things that we're going to have to try and remove when we go through the softening step. And both calcium and magnesium are known as polyvalent cations. Cations are the ones that have a positive charge, and so you'll notice that both calcium and magnesium has a positive charge. So that makes it a cation. What do you think polyvalent means? More than one. You'll notice that sodium isn't on this list. Sodium does not contribute to hardness. So sodium has a valence of 1, but any cation that has a charge of 2 or greater causes hardness. Now, why are we even worrying about hardness? One of the main reasons is that it just feels bad. If you take a shower in very hard water, the sensation on the skin is just uncomfortable. You know, if we get away from aesthetics and get a little bit more into the quantitative side of things, if you have a very hard water, then it doesn't clean things as well. So if you have a bottling plant and you're producing Pepsi or Coke, and you have to wash the bottles like in that video that we watched a few days ago, detergents and soaps don't work as well if there's hard water. And so you can't lather up a bar of soap very easily if you have hard water. And then another engineering reason why hard water is bad is it can coat the pipes and it can coat water heaters. So here on this image I've just put on the screen, you can see here's a pipe elbow, a bend. And on the outside, well, on the inside of the pipe, calcium carbonate has solidified, so now the pipe diameter is so much smaller than it's supposed to be, just because of all this accumulation. Now, this accumulation isn't harmful to people. It's not that this will make people sick, because it's just the same minerals that were in the water. It's that now the pipe is smaller, and there's going to be more head loss through there. And so you're going to lose pressure in the pipes if the diameter is too small. This is showing a water heater, and there's a white precipitate on the elements of the water heater, and that's calcium carbonate that's accumulating on the water heater. And the reason for that is that when you heat up water, calcium carbonate decreases in its solubility, so it precipitates. Okay. The way that the hardness is coming from is when the water is underground. This is a cross-section of the Earth's surface, and then underground, the dashed line represents the water table. So an aquifer is where all of the voids in the soil are full of water. And so beneath that water table, you can see in the subsoil, there's all sorts of things in there. Carbon dioxide is dissolved into the water, and that forms carbonic acid. I don't know if we're going to be able to handle that through the whole class. Hopefully it stops soon. It reminds me when I was working here before, they were building the new extension of the engineering building. You know, this building was only probably a third of the size it was back then, and there were jackhammers going during class. We all got really good at tuning out extraneous noises that semester. So this diagram is basically just showing the water when it rains doesn't have any hardness. It's pure soft water when it's raining, but it picks up the hardness just by being in contact with the soil. So I'm going to go through the process of what chemicals we add to get rid of polyvalent cations. Because if the water's too hard, what we need to do is remove the calcium, magnesium, and other things that are contributing to the hardness. To remove calcium, you have to change the pH to 10.3 to get calcium carbonate to precipitate. And so calcium and carbonate are usually dissolved in the water, but if you get the pH above 10.3, it forms a solid. Here where it says S, that means what used to be dissolved in the water is now a solid. And then to remove the magnesium, you have to raise the pH above 11. So you have to add something, and you can see here they're adding hydroxide to get the pH even higher. I'm going to go investigate that sound. It's driving me nuts. I'm going to pause the recording. All right, that didn't take as long as I was worried it would. All right, so we're going through a chemical reaction to try and get the polyvalent cations out. Between the two, it says here it's cheaper to remove calcium than magnesium. Why do you think it's... We haven't said anything about money yet. Why do you think it's cheaper to remove calcium than magnesium? You're right. So why don't you expand on that? What he said is that the pH is lower to get rid of the calcium. So why would that translate into money? Okay. So whatever chemical we're adding, you have to add more of it to get the magnesium out. The calcium gets out first. And so what's the normal pH of water before we've added any? 7. So 7 is the typical pH. So we're having to put in a lot of chemicals to raise it to 10.3. It's easier to get the calcium out, and hopefully that will be enough. Sometimes there's still too much magnesium, and we have to add even more chemicals to get the magnesium out after all of the calcium is exhausted. When we're adding the pH, HCO3 gets converted into CO3 2-, and this is called bicarbonate, and this is just known as carbonate. And depending on the pH, it naturally shifts between the two. But what you need to know is that we have to sometimes add carbonate to remove non-carbonate hardness. And there's a figure here, a bar chart, that'll help us to understand the difference between carbonate and non-carbonate hardness a little bit easier. Before we look at that bar chart, let's just talk about the chemicals that are actually added to water. Like, what are our tools that we're going to be using? The first of these, calcium hydroxide, raises the pH. And this is a base. Sometimes it's known as hydrated lime. In our in-class exercise, I'm going to say how much lime should be added. We're talking about this. Calcium oxide is sometimes also used, and it's a little bit strange. It's also known as lime, calcium oxide. The thing about calcium oxide is when you add it to water, it turns into calcium hydroxide. And so this is already hydrated. This, when you add to the water, becomes hydrated, and it turns into calcium hydroxide. Also liberates heat. And then if there's non-carbonate hardness, the way that you have to get it out is you have to add some carbonate so that the extra hardness that's in solution will have something to precipitate with. And it's sort of, you need 2 ingredients to get out the non-carbonate hardness. And so to do that, we use sodium carbonate as our source of carbonate. And this is sometimes known as soda ash or soda. So here's the neutralization reaction. It's sort of step by step what's happening each time you add a new chemical. The first thing we have to get rid of is dissolved carbon dioxide. And you know, even if you have a bottle of water or a a container, any kind of water, there's a little bit of CO2 dissolved in it. And that CO2 that's in the water, you can see in this reaction, if you have CO2 dissolved in water, what it really forms is carbonic acid. And so that acid is going to be, at first, neutralizing however much base you add. So we have to add a little bit of lime just to get rid of the CO2. And usually it's not too much. There's just a little bit of CO2 dissolved in solution. So we get rid of the CO2, and then the next thing we do is we precipitate calcium hardness, carbonate hardness that's due to calcium. In bold, it's showing what we've added. Each time during this step of equations, the bold thing is what we've added, and any time it says S, that means that we've removed some hardness, because S is a solid, and the solid will be filtered out, and it's not dissolved in the water anymore. So that's good for us if we're trying to soften the water. So you can see in the second step, we've removed some of the calcium carbonate. Now, magnesium's a little bit trickier. And the reason I say that is it's a two-step reaction to get rid of magnesium. If there's dissolved magnesium in solution, the first thing you have to do is add some lime to get it to magnesium carbonate. And then you have to add more lime because magnesium carbonate, you notice there's no S next to it. Magnesium carbonate will stay in solution. It's not precipitating. And so all we've done is we've changed the form of the magnesium. But then by adding a little bit more lime, it goes into magnesium hydroxide, which you can see does have the S. Now, you'll notice that we were trying to remove hardness, and what did we add? Calcium hydroxide. And that seems a little bit counterintuitive because calcium itself causes hardness. So to remove the hardness, we're adding a chemical that contributes to hardness. And so at first glance, that seems like a little bit like contradictory, like you're trying to solve a problem by adding more of the problem. But if you look more closely, you get the calcium carbonate as a solid, and you're also getting the magnesium hydroxide as a solid. And so for every calcium that was added, you still have a calcium precipitating. So we're not making the problem worse. We have to increase the pH so that the magnesium will precipitate, but the calcium that we added, it precipitates as well. Non-carbonate hardness is where we're adding the soda. And so at this point, all of the carbonate that was in solution has been exhausted, and so to get out more of the calcium or magnesium that may exist due to sulfates, then we have to add a source of carbonate by adding soda, and then also there could be non-carbonate hardness due to magnesium. Okay, so I don't expect you to memorize these reactions. In a quiz or even on a homework or exam, you can refer to these equations to try and understand what's happening. But here's more summary of just the same equations. Here's the bar chart I was talking about. And this is what I would expect you to be able to do, is prepare one of these, given a table. And so let's dig into this and try and figure out what it's actually representing. The first thing is that you'll notice here is carbon dioxide, and they're not listing carbon dioxide as an anion or a cation. The rest of this graph is segmented into the positive charge on top and the negative charge on the bottom. But carbon dioxide goes across the entire width of the bar chart. The reason why we have to keep track of carbon dioxide is that until we neutralize this, our pH isn't going to change. So all of the lime that we add until the carbon dioxide is used up is going to have a steady pH. So we'll use up this just to get to 0. And so what you'll notice is that there's an axis going to the right, and these numbers are increasing. But 0 is at the rightmost edge of the carbon dioxide. And so the interpretation of that is that until you neutralize the CO2, you're not going to be able to start removing any of the hardness. So let me just summarize that on the board. So here is our hardness. And we're going to be adding more and more lime, but until we use up all of the CO2, we don't start to remove the hardness. And so how much lime we add is going to include the CO2. Now, since these are all listed as CaCO3, it allows us to do things that are pretty nice. Like we can say how much Ca calcium hardness there is. You just notice it's 149.2, 149.2 milligrams per liter as CaCO3. And then the amount of magnesium that's present, you just subtract the 215 and the 149.2. And so 215 minus 149.2 is going to be 65.8 milligrams per liter as CaCO3. So that's how much magnesium there is, and likewise with the sodium, you just subtract the beginning and the end, and that tells you how much is in the solution. So here, the numbers were given, and that's how the chart was created, was adding up all of the positively charged cations, and it goes here to 232.4, and in the anions it also goes, when you add them all up, to 232.4. Sometimes it'll be a little bit off, just because all of these are measured quantities, and if you're doing an analysis, you may get a slight imbalance in the charge, and that's normal. It doesn't necessarily mean there's a mistake in the calculations. It can just mean that there's some imprecision in the lab tests. So from this chart, the carbonate hardness is interpreted as, so carbonate hardness is abbreviated CH. And the carbonate hardness is this anion, HCO3, is our carbonate hardness. And so we have 185 milligrams per liter as CaCO3 of carbonate hardness. And then non-carbonate hardness what's our total hardness from this chart? Do you know what our total hardness is? The total hardness, actually, remember, it doesn't include sodium. So it's just the total amount of the bar chart through the calcium and magnesium. Yeah, so the total hardness, so T total hardness, TH is 215 milligrams per liter as CaCO3. The carbonate portion of it is 185. So NCH, non-carbonate hardness, is the total hardness minus the carbonate hardness. So the total was 215 minus 185, 30 milligrams per liter as CaCO3. So these bar charts are useful because it helps us to visualize where the hardness is coming from. Some of it's coming from carbonate sources, and some of it's coming from non-carbonate sources. In today's in-class exercise, you're going to have to find out how much non-carbonate hardness to remove. Now, you don't want to add any more chemicals than you have to, because chemicals cost money. And so it'll usually be a policy decision on how soft the water should be. And basically, you want to take the hardness low enough that it feels comfortable on the skin, low enough that soaps and detergents are working okay, low enough that it's not going to cause clogging of the pipes. But you don't want to take it all the way to 0, because actually if it's too soft, people will start to complain then as well. So in the problem statement, it'll tell you what's the total hardness that you can finish at. Some of that total hardness will be carbonate, and some of the total hardness will be non-carbonate. What this equation is showing you is that the amount of carbonate hardness that should be removed is the initial amount that was present. And in this bar chart, we should call this NCHI, because this is the initial non-carbonate hardness before we did our reactions. The final amount is going to take into account how much carbonate hardness is there after the reaction. So the best way to illustrate that is for us to take a look at the in-class exercise. In the in-class exercise, we're going to go through this flow chart, and I don't want to say too much about it because I think that the best way for you to understand the flow chart is to put some actual numbers through it. But here is our water diagram, and the first thing you need to do is prepare a bar chart in the same way that we had a bar chart on this slide. So for the in-class exercise, take the table of water chemistry values and prepare a chart like this for part A, and answer the questions like what is the initial carbonate hardness, the non-carbonate hardness, and then go through D. This flow chart will tell you the amount of lime required. So work together with your friends on parts A through D, and then we're going to do part E together because it's a little bit tricky. Of course, you're welcome to try part E, but it takes a little bit of experience to know the amount of soda that's required. So just A through D for now. All right, let's take a look at the bar chart. A lot of you have already noticed that the cations and anions don't add up, and that's pretty common. Think about where this value would come from. Somebody took a sample of water and they're doing testing on the sample. They're running it through an analyzer, and the machine maybe is more accurate at measuring calcium than it is at sodium. You know, machines measure things sometimes with some error. Like if you're measuring the pressure of your tires, your gauge maybe has 1% error. If you're measuring the weight of something, a scale can have error. So whatever instrument was used to measure these in the water probably had some error, and it looks like when you add it up, there's 490 milligrams per liter of cations and 489 of anions. And so that's okay. Don't be thrown off by that. So the first thing that we graph is the carbon dioxide, and there's 55 milligrams per liter of that. Then the next thing, we always have these ions in the same order. Have calcium, then magnesium, then sodium. Do it in that order. And for the anions, do carbonate, sulfate, chloride. Now, this chart has different overlaps than the other one did. If we go back to the first example we looked at in the notes, that bar chart, the carbonate was bigger than the calcium. That's not the case in what we're doing now. In this one, the calcium is bigger than the carbonate. All that means is that some of the calcium is coming from sulfate and some of the calcium is coming from a carbonate source. So what questions do you have about the bar chart so far? All right. In part B, it's asking what is the initial carbonate hardness. It's 277, right? And the reason why is here's our carbonate and here's our hardness. On the top, the hardness is from here to here. It's from 0 to 411 is our hardness. How much of that hardness is from carbonate and from non-carbonate? And so let me write directly on the whiteboard here just to make it even more clear. Here's what we could say is our hardness. our total hardness goes from 0 over here to 411. Why don't I continue beyond 411? Because sodium, Na, is monovalent. It's not polyvalent. And so however much sodium there is does not contribute to the hardness. So our total hardness is the sum of the calcium and the magnesium. Okay? Now, of this total, here is our hardness. This much of it is our carbonate hardness. So here is our CH, our carbonate hardness. And then the non-carbonate hardness, I'll just put little dots in for that to shade it. This is NCH, non-carbonate hardness. I don't know if that makes it any clearer. It looks a little bit sloppy. But the point is that you have to look below the cations at the anions to see whether it's from carbonate source or non-carbonate source. Okay, so in part B, it's asking what is the carbonate hardness, our initial carbonate hardness before we soften. So CH sub I is going to be 277 milligrams per liter. And then in part C, what did you get for our initial non-carbonate hardness? So it's the total hardness, which is 411, minus 411 minus the carbonate part. So the final amount that's remaining is 134 milligrams per liter. All right. Now, how much lime required is where we go through the flow chart. And in the flow chart, you start at the top. And it says, how much lime should you add? Well, first of all, you have to add enough to cancel out the CO2. And what's our CO2 concentration? Okay, so we add 55 milligrams per liter of lime. And now it's saying add enough lime to cancel out the HCO3. So we look on here, where's our HCO3? There it is. So also add another, on top of the 55 you already added, add more, 277. Now it asks us a question. It says, is the concentration of magnesium greater than 40 milligrams per liter? So we go to the table, look for magnesium. It's 78. So since it's yes, I circled that, and it takes us to this next, the next amount of lime we should add. It says add as much lime as magnesium minus 40. So over here, 78 was our magnesium. So it's saying add 78 minus 40. So now we should add 38 milligrams per liter of lime. And now we have another question. Is magnesium minus 40 greater than 40? So it's asking, this amount here, is 38 greater than 40? No, 38 is not greater than 40. And so it asks another question now. It's asking, is your magnesium minus 40 less than 20? So is 38 less than 20? No, so that sends us here. And it says add lime equal to magnesium minus 40. Now this is the same amount as we just added. So that could be confusing. You could say, well, does that mean just the original amount is enough? No. What it's getting at is back here to our reactions when we were looking at this one. We had to add, when we're considering the magnesium, we had to add lime 2 times. Once to get it from magnesium to magnesium carbonate, and then another time to get from magnesium carbonate to magnesium hydroxide. So it's going to be 38 plus 38. So back here to the flow chart, we get 38 at this stage, and then another 38 here. This phase right here is sometimes called the excess. And you can see that I've highlighted that on the slide, the in-class exercise. I've put the dashed line around it. How much lime excess do we have to add? So we added this much lime here, and then we add a little more as the excess. And in our case, it's 38 for the excess. Any questions so far? You're going to use the same kind of idea for the last two problems on the homework. So far, though, we haven't made any use of the information it says here that in part E, we want to, how soft do we want it? We don't want it to get down to 0 softness. In part E, it says get it to a final softness of 85 milligrams per liter of hardness. So that's how much hardness can remain. What was our initial hardness? When we first got started, the total hardness was 411. So 411 is our starting hardness. 85 is going to remain. Now there's an assumption that is often made, and that is that some of the reaction won't go the way it should have. Like, remember we talked about rapid mixing, and some reactions are so fast that if you don't mix it in correctly, then around the edges of the reactor, the reaction won't happen. So let me do a drawing just to illustrate what I mean by that. If we had a reactor, and here's the water, here's our impeller, and we're putting in, here's our lime. And what if the reaction only gets around here? And then in the edges, there's a dead zone where the hardness, the carbonate hardness that's in this dead zone, it doesn't get removed. And so there's a little bit of carbonate hardness that sneaks through the process. And in our in-class exercise, it says to assume that 40 milligrams per liter of the carbonate hardness is remaining because of incomplete mixing. And so what we have to do is do calculations of our non-carbonate hardness, initial, and final. And so I'm going to walk you through this. We're going to go through it all together. Our total final hardness, it says in the problem statement, 85 milligrams per liter. That's how much we can have at the end. And we're going to assume that 40 of that is from a carbonate source. So 40 is carbonate, 45 is non-carbonate. Total 85. So non-carbonate hardness, the final after all of the reactions, we're going to have 45 milligrams per liter of non-carbonate hardness, and 40 will be carbonate. And so the amount that we have to remove, NCH subscript R, is just the initial amount minus the final amount. So we initially, in part C, you calculated that there was 134 milligrams per liter of non-carbonate hardness to begin. In the end, we want 45, so we have to take out 89 milligrams per liter of non-carbonate hardness, and that's how much soda you'll add. Yes? Let's say yes. I mean, it really depends on how good your reactor is. You know, like if we had, do you remember seeing a picture of a reactor that looked like, we had one reactor that had a central shaft and then blades like this. And the water's coming in and the water's going out, but we were injecting the chemical in 3 spots. So a reactor like this would probably have more efficiency, and so it would be lower than 40. But for now, let's just assume 40. You know, that's really what you're asking, is like for the homework and so on. Yes, you can assume 40 is how much of the carbonate hardness sort of sneaks through those earlier reactions.
So we don't have to assume the numbers are true.
Well, I mean, they're given based on an assumption. Yeah. I mean, they're given in the problem statement here. I don't remember from the homework if it says a different assumption or what. If it does, in the homework, if it doesn't tell you what to assume for the carbonate hardness that sneaks through, use 40 milligrams per liter when you're calculating the amount of soda. Yeah. So this one, this 134, is coming from, if we look at the bar chart, the non-carbonate hardness is the hardness from here to there. So 411 minus 277. So the total hardness was the calcium and the magnesium, and then subtract however much HCO3 there is. I have here the in-class exercises from last time and your quizzes. So please pick those up from the table and put your in-class exercise from today onto the chair. Yeah, sure. Thanks. I hope you have a good weekend. I'll see you on Sunday.